Usually, when talking about oscillators, the first thing that may come to your mind is crystal oscillators that feed microcontrollers with clock. And when looking at a crystal oscillator, you will see a number that makes it special, which is the waveform frequency that it can generate. Today in this video, we will build an astable multivibrator circuit using transistors, discuss the working principle of it, and we will even take this oscillator to the next level and build an electronic bagpipe. We are going to listen to different levels of frequency today, so get ready and let's start our video. Before diving into our topic, I want to let you know that in my next video I'm going to share more oscillator based circuits, so make sure that you subscribe to this channel and turn on the notification bell so you don't miss anything. Now, to understand the working principle of this astable multivibrator oscillator circuit, let's have a look at its circuit diagram. At the first look, we can say that this is nothing but an SR latch. So to have better understanding, let's see how this latch circuit works. When connecting this circuit to a power source, definitely one of these transistors will conduct. So let's assume that the transistor on the left hand side will conduct first. In this case, the output Q will have logic 1, while the output Q complement will have just the opposite logic signal, which is logic 0. This happens because while this transistor is conducting, the terminal Q complement is shorted to ground. In the meanwhile, the other transistor will be derived to ground, so it will be turned off. That's why at the output Q we will have around 5 volts, which will light up the parallel LED. Remember that the left-hand side transistor base current flows through this branch, so if you had a series LED in this branch, it will light up slightly. When pressing on the reset button, the left-hand side transistor will be derived to ground. So at this point, the terminal Q complement will have logic 1 because in this branch, the right-hand side transistor base current will flow, which is relatively small, so it won't cause a significant voltage drop at this resistor, and around 5 volt can be observed at Q complement terminal, which will turn on the right hand side transistor, shorting this LED, so we have logic 0 at the output Q. Of course, this LED will light up for logic state indication. Pressing on the set button will return us to the first state, where we have logic 1 at Q terminal and the opposite at Q complement terminal. Remember that at this point, pressing again on the set button will do nothing, because the right hand side transistor is already derived to ground. As a final note, I noticed that many people on the internet consider this circuit as a flip-flop, but it's not, because a flip-flop has a clock input feeding it, while latch circuit doesn't. Alright, we are done with the theory now. So for the sake of demonstration, let's build up this circuit on a breadboard and see how it will perform. You may wonder why would I connect an oscilloscope to such a circuit, right? Obviously, with such a setup, we could get rid of switch bouncing by transforming a mechanical switch to electrical switch. That's why the transactions between voltage levels are perfect. To learn more about switch bouncing, you can watch switch bouncing and debouncing circuit episode from the card shown above. Before diving into the concept behind this circuit, let's agree on the fact that capacitors are considered as open circuit while they are fully charged and short circuit when they are fully discharged. To show you this in practice, I conducted a simple experiment where I set the voltmeter on continuity test and connected its probes to the capacitor leads after flipping it. You will notice that the multimeter is giving a beep sound at the instant a contact is constructed, indicating for a short circuit, because the capacitor is fully discharged. But after a very short amount of time, the sound disappears, indicating for an open circuit, because at this time the capacitor is charged for the same level that the multimeter is supplying for conducting the continuity test. Okay, now it's time to make things a little bit harder. by moving to this Astable multi-vibrator oscillator circuit, which works similarly to SR latch. But here, we don't have input signals, set and reset. So this time, just like we did with the SR latch, let's assume that the left-hand side transistor is turned on. Because anyways, when connecting this circuit to a power source, one of these transistors will be turned on. So at this point, we have the following outputs. Okay, now this capacitor will start charging until it reaches the right-hand side transistor on voltage, which is typically 0.7 volt. Now let the game begin. When the right-hand side transistor is turned on, the terminal Q is shorted to ground. At this instant, the left-hand side transistor will be derived to ground, leading it to be turned off. Now this capacitor will start charging until it reaches the forward biasing voltage of this transistor, which will turn it on, and the other transistor will be derived to ground, leading it to be turned off. In this way, you will have two infinitely alternating outputs. Remember that the oscillator switching frequency depends on these components due to the RC time constant. Keeping both circuit sides symmetrical will give you a signal with 50% duty cycle, and any imbalance in the circuit will change that. In my test, I selected 1 microfarad for both capacitors and I could get a frequency close to 300 Hz. The problem of the output right now is that it's not a square wave, which is not desired at all. So as a quick solution, I added two NPN transistors to the circuit output so that the charging and discharging of the capacitors doesn't appear at the output. I also lowered the capacitor's value to 0.1 microfarad to get higher switching frequency. Adding parallel LEDs to the output transistors and lowering the switching frequency will flicker the LEDs continuously. Finally, we have reached the monster level. Alright, that was scary, but hold on, we have already covered everything related to this circuit, so no need to get scared, because the only extra thing we have here is a voltage divider and a potentiometer. The main idea behind this construction is to cause an imbalance to the circuit and to change the capacitor charging voltage to modify the output frequency when pressing on one of these buttons. In this circuit normal state, the oscillator doesn't work because the right-hand side transistor base is not connected to the power source. Now let me tell you how it works. For example, when pressing on this button, a voltage of 2.25 volt will be formed across this resistor, and pressing on this button will form 4.5 volt across the same resistor due to the voltage divider. This change in the capacitor supplying voltage will lead to form different levels of frequency at the output, which means different sound. For demonstration, I constructed this circuit on a breadboard and let's see how it will work. This potentiometer is used for sound adjustment. Now it's time to make this circuit permanent so I can play annoying music when I want. This brings me to the end of this video. I hope that you have learned something new from me. If you like this video, please like, share and subscribe. And let me know your opinion in the comment section below. Stay tuned and see you next time.